don't confuse them, are going to present Flattening the Curve, Rediscovering Web UI through Historic Geometric Constructions. And they're both developers and software people and interested in historical stuff. So please take it away.
Thank you. Thank you for coming today. Good morning. Liry and Mia present Flattening the Curve. So, Web UI. Probably a lot of you have already thought about how does it actually work behind the scenes, because you're hackers, you're programmers, you want to know how stuff works. But today we're going to show it to you from a different angle. We're going to show you the trajectory of historical progress of how the Web UI came to be what it is today, how it works behind the scenes, or at least a small part of it.
So my aim here, so the next slide, please. No, next slide, okay. So my aim here is to show you the more historical part of it. I want to encourage you to think of yourself as a one person in a long lineage of engineers that really shape the way mathematics looks today. We're using the curve as a use case for something that people thought about since antiquity in different ways, as astronomers, as architecture, in thinking about perspective. But at the end also as thinking about Web UI. And you as someone that is like developing, shaping it. So we will try to convince you in that. So as I said, my name is Mia. I'm a history of PhD student by day and a software engineer by night, or vice versa, who knows?
Hi, I'm Liry. I'm an artist, designer, and also a software engineer. So, now we can get started. Web UI. So, as you all know, the web, when you are surfing to some page, there's a lot of stuff that's going on. But we argue that one of the most important thing is the graphics. How are things shown on your screen? This is a very general problem, and we're focusing here on web, but a lot of what we're saying will be applicable also for mobile, for desktop, for a lot of other stuff, but the motivation is clear. We want to show stuff, we want to show them pretty, whether it's text, images, or any other thing that you are seeing on your screen. In this talk, again, we will focus mostly on images. And when we're talking about images, we need to ask ourselves, what is an image in a digital point of view? So first of all, we have how the image is represented, what's its presentation. To have an image, we need to encode it in some way for it to be stored, for it to be transported, streamed, for the site to be able to show it. That's one side. The other side is rendering, actually showing the image. So we need to take what was encoded in a binary format or whatever, and to actually show it to you. So the problem of showing, called rendering, is a very complicated and interesting problem. And it's done in a lot of different ways, but they're sort of similar. We're not going to get into that today. Stay tuned for the next convention. We'll focus, of course, on the first part. And we'll start with the basic and most intuitive solution to how to store an image using pixels, pixel-based images. We have a lot of small squares that together make up one full picture. So if we zoom in, we can actually see these pixels. They could be represented as a bitmap, just a large matrix of colors saying what we should present. Of course, we could compress it. We could do all sorts of cool stuff. But basically, all the image formats that you know, PNG, GIF, and all sorts of stuff like that, are using the same basic principle of raster, of showing images using pixels. What are the problems with this approach? We have several issues that we can think of. We have a lot more, but we'll start with these. we have scalability in the terms of file sizes. If we have a very good image that is very high definition, the file might be very big because we need to represent a lot of pixels if we want to actually have this high definition. Also, we have scalability in terms of display, right? If we are not on this too small screen, but on a very big screen, images might not show up beautifully if we don't know how to scale them. If we have pixel-based images, scaling them is not that simple. Of course, there are a lot of algorithms, optimizations, but it's not out of the box. Again, what we don't get out of the box is all sorts of editability and customizations. It's not straightforward to take pixels and turn them into other stuff like changing their colors. You might think of several solutions, but it's not too intuitive. And these are the disadvantages of the raster method. Enter SVG. SVG, Scalable Vector Graphics, comes to answer some of these concerns. Of course, it will have its own problems, but today we will focus mainly on the positive side. So, scalable vector graphics, XML formatted file to represent images. So, for example, in this very short SVG, we can see that we have a definition of 3 circles. They have certain positions. They're shown on the page. We're not going to get into too much details right now. Let's see another example. I want to draw a very simple W character. What you see here is one definition of a path. A path is just a command that tells SVG how it should be constructed. Construction, that's a very important verb. You will see it a lot, stuff being constructed across our talk, so don't get tired of it just yet. What we see here is a list of instructions that tell the rendering engine what it needs to do in order to display this W. So in this case, it's not too intuitive, but if you take a deeper look, you will see that it's quite simple. We're drawing a line that goes from here to here to here to here, and we're drawing a W. Very simple. But of course, we want to show you complicated stuff, right? We want this beautiful, fancy, Gothic style W. We don't want like straight edges. So to make that work, we'll need a bit more work. This looks very complicated. It's also very shortened. It's about 2,000 characters to show this W, which is not a lot, but it is not something that you can intuitively look at and understand. But given some ideas, you will find that it's not that complicated. And the next time you're going to look at one of these after the talk, we hope that you will also find that it's quite intuitive, actually. The actual magic is done using something called Bézier curves. Sorry if we're mispronouncing it. We have lots of apologies of mispronunciations, but we'll probably make them each time, so don't get tired of that either. So, how does this work? How does this magic actually happen? Well, for that, you will need some more background, because we don't just want to instruct you on this should go there and this should go there and wow, you have a beautiful line. We want to show you how this came to be. What's the historical trajectory, as we said, that made this what it is today. So far, we've looked at the problem. We want graphics, specifically web UI. The first approach, the simple raster pixel-based. Then we introduced SVG.
Oh, but wait, curves. How do they? How do they even work in SVGs? So my take here is that I load you in with SVG. We load you in with SVG, but I don't really care about SVG. I care about the history of mathematics. So, mathematics, a very, very bizarre monster that we try to tame, express, look at from different angles. And many people looked at it from different angles. We have people that are thinking about curves from antiquity. And they're looking at it when they're thinking about astronomy, when they're thinking about shipbuilding, when they're thinking about architecture, when they're thinking about abstract algebra. But curved lines really resist simplicity. And we want to ask ourselves, how can we create them on a page? How can we express them? And how can we create them on a computer? So my approach is, not only my, but many people's approach is that what created curves throughout history is not only like development of mathematics, yeah? There are many, many factors that shape the way we shape curves. They shaped our approaches to curves and to other subjects in mathematics as well. By example, society and economics, theory and curiosity, material constraints, for example, paper versus computer, and real-world problems, architecture, astronomy, looking at the sky. It's not limited to this, but it's a solid lineup. So, it's not only mathematicians that like thought about curves and then implemented it in technology. We many times we think about it that way. Like there are stuff that are done in academics, so academics like to think about it that way. There are like complicated theoretical stuff done in academics, and then engineers get them and they implement them. But it's not. I don't think it's like that. I think there is, and I want to convince you, that there is sort of a feedback loop. But it's not really a feedback loop. It's more like a spaghetti sort of feedback, because many stuff are like interconnected here. So, as always, we want to start from, this is like our timeline for the curves. So we will start from the ancient Greece. These are like some points of like stuff that are interesting, but many other stuff happened through our time, but we're not going to discuss it. But believe me, it's not the only interesting stuff. Just 5 interesting points. So we'll start with ancient Greeks, then we'll go to the 16th century and talk about 2 interesting people. Dürer, which again mispronouncing, sorry, I don't know umlaut, too hard for me. Dürer, that he's like a really cool artist, and Kepler, which maybe you know from Copernicus and astronomy and all of that. And then we're going to go to the 17th century. We're going to discuss Descartes, which you might have heard of, Cartesian lines, and I know cogito ergo sum and so on.
I think, therefore I am.
Yeah, that one. And we're going to finish with the car engineers and SVGs, because like we load you in with SVGs, so we have to like come back to it at the end, at least for me. So let's start with the Greeks one, the Greek people. So next. Thank you. So what's really important to know about Greek mathematics is that there is this kind of very pure construction, which is the straight edge and compass, or ruler and compass. So think about everything you can create with using a ruler and a compass, okay? And these are like your only 2 tools to create, to construct the geometrical shapes. And this is like the very pure construction, the perfect, like this is like how you should do it, yeah? I'm like doing some simplicity stuff, but fine. How would you create a 12, a polygon with 12 angles, with 12 sides, using just a compass and a ruler? You don't have, like, you can't calculate the angles. It's not allowed. Like, maybe you can construct something from a ruler and angle.
Remember, we don't have trigonometry at that point. We can't like just take pi and do pi by 12 or something like that.
Like you can sort of create it, but it would be very anachronistic reading of the Greek geometry. So we can you can see here how you can do this construction. I'm not going to do it step by step, but you are like creating a circle, then you are creating arcs, and then you are creating more arcs, and at the end you're actually like sectioning this circle into 12 equal parts, equal arcs, and then you put the sides.
Note that the auxiliary lines are at the end removed. So we have a lot of construction that is made to get to the actual target, right? That's an important part. We are not cheap on making lines. We need them. It's really a part of the process.
So, the ancient Greeks came at some point to 3 problems, the big 3. They came into more problems, but we are like really simplifying it. 3 problems that they just couldn't solve with just ruler and compass construction. So these are the big 3. They didn't succeed to construct a square with the same area as a given circle. You can try to think to yourself why, but think about it later. Or now, I don't know. Doubling the cube. So if I have a cube, it has certain volume. Now I want to create another cube that has double the volume of the first cube, and I want to understand what is the size of its edge. Also, couldn't do it with a ruler and compass. And trisecting the angle. So how can you have an arbitrary angle and you want to cut it into 3 equal parts. So they couldn't do it with a compass and ruler. Just couldn't. Now, today we know that these problems, you can't really solve them with a compass and ruler, but they really, really tried. Now, although they had this very pure compass and ruler stuff, they also had some, and we will call them cheats. So one cheat like that is motion. So if you like say, I'm moving the compass, I'm moving the page, I'm moving stuff, yeah, I'm moving in a continuous motion, whatever you're doing here, you can maybe build some stuff. So this is a spiral, for example.
The Archimedean spiral. Remember it? It's important for later.
And another really, really, I'm calling it cheat, but again, I'm feeling like bad that I'm simplifying stuff too much, but so sorry. So let's call it a cheat for this purpose. You can think about taking a cone and slicing it with a plane. So here I have a cone, which is something I can easily build with a compass and ruler. Yeah, it's okay that it's 3-dimensional. It's a solid. And if I pass a plane through it, I can cut this cone in many different ways, create what we would call a parabola, what they would also call parabola, hyperbola, ellipse, etc. So our 2 big guys that did cones, other did it as well, is Menachmus and Apollonius. And Apollonius, once we have a ruler that he wrote somewhere, that the subject of conic section is one of those which seem worthy of study for their own sake. Okay? So, if you remember my before that I said, that we have 4 factors. Yeah, this is important. So, if you remember my 4 factors, one of the factors there was, one of the things that shapes the shape of curve is our just curiosity. Yeah, people want to do mathematics because it's fun, because they want to discover stuff, because they like to play with lines. So a lot of the Greek mathematics that survived is like more of the highbrow, and we see like people that are more like doing the stuff like Apollonius. But please remember that absence of evidence is not an evidence of absence. So maybe there were other stuff that people use geometry. Just, it is like 2,500 years, so who knows? We do have some stuff, astronomy, architecture, other stuff from the time. And what I want to say is that, hey, all of this stuff that happened with curves, the big 3 problems, a little bit shaped them, a lot shaped them, and astronomy and architecture. So we have here 2 factors that we see in play, okay, for shaping our approaches to curves. What did we see in this first part of our timeline of ancient Greek? We discussed the pure construction of ruler and compass, the big 3 problems, and 2 cheats for curves. Again, simplifying stuff by a lot, but it's fine. Motion and plane section of solid figures. Now, we are going now to jump 1600 years to the future, something like that. Okay, 1600 years to the future. But a lot happened during that time. Okay, so I don't want you to feel like nothing happened and everything was stale and the like Middle Ages is like a black period or something. No. Like many stuff happened. We're just like skipping them to have a talk that is like 50 minutes. So we are now in the early modern period. Bonjour. 16th century, and we are going to talk about our next point here, which is Dürer, who drew curves and he also printed them. Not him exactly, he did not do the printing because this is like someone that got lower wages did it, but yeah. Hello Nuremberg, someone more German can say it probably better. Okay, Nuremberg, this is how I say it. We are in the German Renaissance. Lots of stuff. This is like one of the places to be there in that time, and many is like it's a very nice place. Like stuff happen. Print is a new thing, and it's really spreading in Europe more faster than the Black Plague, really. And we have this guy. You might know his paintings. He's like famous painter as well. He did painting. He was also like he really did beautiful stuff for print, because for print in the beginning of this like print age, you needed also visualization. Why? You need to for many reasons, but you also like we said in web graphic, you want beautiful stuff. In print, you also want beautiful stuff. You want to print beautiful stuff. You don't want only to print letters, right? And also to print letters, it's difficult because you need like many different kinds of letters. You want like titles. You want. So, again, not reading it in German. Dürer also wrote a book. He like did lots of stuff, but he also wrote a book, which is my favorite of his. Who knows why? Which is called Instructions for Measuring with Compass and Ruler. I hope it's a good translation. 1525. And one of the stuff that he wrote in this book is that the ancients have shown that one can cut a cone in 3 ways and arrive at 3 different shaped sections. I want to teach you how to draw them. So Dürer was more interested, in general, simplifying, whatever, was more interested about like how to draw the stuff, how to actually construct them on a page, than on the like rigor, geometry, having it like what is like the theory behind it. He was more like in this book, let's like instruct people how to do it. So, Liri, how can you draw a spiral, please?
So we're taking you back to the Archimedean spiral. And Dürer gave us instructions in his books about how to draw many stuff. As Mia told you, he was more focused on actually giving you instructions, sort of algorithms, point by point, how to do stuff. We're going to show you one example that will be made up of several parts. We'll start with the spiral. So Dürer is instructing us on how to create the spiral. I'll take you through it quickly. Don't worry, it's very fun. We're starting with a blank canvas. We're taking 2 points, A and B, and drawing, using our compass, a circle with the center at point A that goes through point B. Then we're going to draw a 6-sided polygon. Now, you already know that you can do it with compass and ruler. I'm just saving you the time because it's a lot of doing circles and erasing them. We are also using this 6-sided polygon to actually get to a 12-sided polygon because we want better accuracy. You will see it in the next steps. We can get rid of the circle, and we're going to draw lines using our ruler from each of the 12 points back to the center, and we're going to number them from 1 to 12 and use a ruler that is already being divided to 12 equal parts, okay, like our circle, the same 12, and we're going to use it to go over each of the points of the circle and draw a dot where the index of the ruler matches the index of the line. So the first one would be 1 and 1. The second one would be 2 and 2, and so on. So you can see that we're actually getting quite a nice spiral shape. Let's get rid of the auxiliary lines, and we're seeing the dots. So Dürer tells us this is how you get the dots. Now, how do you actually get the curve? So you can't do it with a compass, okay, because these are not circles. If you will try to draw a circle from one point to the other, it won't give you a nice spiral. So what Dürer tells us at this point is to eyeball it. Just draw a nice line between them. You have the points, and you can actually make it up yourself. So that's what we did, making it up ourselves, and we actually get quite a nice spiral. Dürer is telling us that we can use more points to get better accuracy, meaning the more auxiliary points we're using, for example, 24 points instead of 12, and we will get a nicer spiral. We will need less eyeballing to actually make the curve happen. Next step, Dürer is taking this spiral and is making it prettier. He's only using it as a base to actually make more pretty stuff. So for example, how did he make this beautiful petal shaped spiral? So actually it's quite simple. We're going back to our dots and the spiral line, and we're using circles with a simple compass to actually create these petals. So I won't take you through the whole process, but basically we're using the points as guiding anchors to create circles, and we are intersecting the circles to create nice petals. So we're doing it step by step, and quickly enough we got the petal shape. Very cool. Again, you could do it with 24 lines, with 48 lines, and you will get much prettier shapes, and you can take it however direction you actually want after that. But Dürer didn't stop there. He took this spiral and he wanted to make a different curve out of it. You see the curve on the right. How do we get to this curve from the left one? Sorry, from the one on the previous construction. So now we're taking our spiral, our auxiliary lines again, and we're adding more numbers. We didn't construct anything new yet. We're still using the same points. We just went numbering them up to 24. So we have the 12 on the circle, and we have the 12 of the spiral. Together 24. Now we'll take a straight line and we'll also divide it to 24 equal sections. Now what we want to do is again to cross section the 1 and 1, the 2 and 2, and so on, and create auxiliary dots to understand where stuff are meeting. So we'll draw the horizontal lines, then we'll draw the vertical lines. Once we get all these lines, we can tell actually where they are meeting. Draw these points, right? And you can see a very nice curve that you might find a bit similar from stuff you know. It looks a bit like from physics, but we don't know whether Dürer had thoughts about that. Again, to actually make this beautiful spiral, we still need to connect the dots. We don't have any trick for that. You will need to have an artistic hand. The last point that Dürer actually made with this is taking it another step further. This time we won't take you through the whole steps, but we will tell you how he did it. He took a protractor that shows the angles. He sectioned it to 60 equal parts. So you can see on the right how taking a full length of the ruler and matching it to each of the angles that make up the 60 degrees, right? Like 1, 2, 3, and so on, and where they are intersecting with our ruler to make up these 60 points. Then we're going to cross them with our spiral from before to actually make this beautiful, beautiful thing. Now, what is it? I don't know, it's just beautiful. We're taking each point, we're using it as the center of a circle to create this magnificent piece. Dürer also did other stuff. He, for example, invented this beautiful 3-part compass that helped him create more complicated things, but we won't get into that.
So what's important to know is that like the rigorous part, he was like less into this rigorous mathematical thing. For example, in one point, he is just writing that he is implying that every shape that has equal sides is also has equal angles. But in fact, this is not true. If you look here, I have equal sides, not equal angles. But he is implying it in one part of what he is writing. So he is more into the construction, less into the rigorous proving stuff, okay? However, in the 16th century, a little bit towards the 17th century, we have one more guy that we want to introduce to you, because one is not enough. His name is Kepler. You might know him, but to understand what we are talking about with Kepler, I want to get you a little bit before, all right? So if you look at the sky, and this is something that the ancients did as well, you will see that if you every day you look at a planet, for example Mars, you will see that it moves a little bit. It is not moving like this in the sky from that point to that point, but it is going a little bit backwards. So if you think about a model where Earth is in the middle and the stars are just around it, then it doesn't really make sense, right? That there is this motion backwards. This is from 2018. Each day is marked here. So already in very old models from Greece, already like thought about it. They saw it and they also discussed like how can it be. So for example, here you see Earth is in the middle. You have, I'm not really going to go into it, but you have two circular motions that can account for how, for example, Mars, the trajectory of Mars and their motion backwards. This model and other models were evolved during the time. For example, this is from the 13th century. You can see stuff got complicated. And Copernicus in 1543 said, hey, what if we just change the perspective? So he didn't, again, simplifying like hell, I'm sorry, but what if we just change our perspective? What if Earth is not in the middle and everything moves in this like multiple circles, very, very complicated motions, but the sun is in the middle, but everything is the same. You just change the perspective, right? And if the sun is in the middle, and then everything just gets simpler. So it's less, what Copernicus did is less than an innovation in the sense of like, he had new measurements and understood stuff, but more into just, hey, if I'm changing here the perspective, the motion becomes simpler. It's simpler to understand it, right? So you think about relative movement, right? Like trains that are moving. Are you moving? Or the two trains are moving, or only that train is moving? So Kepler, what was his title? Royal mathematician, imperial mathematician to the royal something. He was like important person, okay? He was like very like imperial mathematician something. And he, like the problem with the model of Copernicus is that it didn't explain some of the movement, in particular the movement of Mars. Why the movement of Mars was not explained by this? this movement backward was not really explained. It didn't really match the details. It didn't really match the details. And then Kepler said, haha, what if this is an ellipse? And then stuff are working. So this is from Kepler's book. You can see Earth is in the middle, and this is the trajectory of Mars, which is this beautiful thing. And what's interesting is that Kepler mentioned Dürer. So this is like how it looks like. We can move past. Past. Okay. What I want you to remember, 16th century, many people are doing geometry. Curves are looked at from more practical perspective and more like astronomical perspective. But there is some connection. So like people are, again, with this crossing, looping thingy, yeah? And let's go to the 17th century. Do it really quick. Descartes, you might know him. And his one of his big innovations is saying, hey, we can think about a grid, our coordinate system. So what is so interesting about a coordinate system? One of the things that is so interesting about it that it mixes two concepts. The first concept is, again, concept from the Greeks, locus, the concept of locus. Locus is just a set of points that are satisfying some conditional constraint. And then you can think about equations. Equations are many stuff, but one of the ways to think about equations is as a way to express numerical relationship. For example, number of potion brewed multiplied by price per portion equals the wage income. So this is like sort of an equation, sort of, yeah? Now, if we combine the two, if we have this Cartesian coordinate system, we can think about like this kind of equation that have a geometrical representation, because the x and the y, this number of potions and all of that, they have a meaning, a geometrical meaning on the page. Yeah? Like you have here the x and the y. They have a meaning on the page. You have a geometrical meaning. You can explore them in geometrical means. On the other hand, you can take a geometrical shape and try to think about it as just a representation in this set of like the relationship between the x and the y. So what he did, this crossing of algebra and geometry, which was a like really like new thing, like in a sense, during that time, is one of the stuff that were like enabled or were part of calculus. So again, we see that people are thinking about curves, this time in a more abstract kind of way. So yeah, this is...
Okay, let's get to the actual modern stuff, not early modern, actual modern, and talk about the current genius and the computer-aided design. We're getting finally back to SVG, no more history, well, a bit more history. Let's make sense of this. But first, we need to understand why we're seeing what we're seeing. Why does it make sense? I promised you that all along, but now it's really going to make sense. In the 40s and 50s, the car industry was booming. Engineers were working with blueprints, like doing stuff by hands. They were very accurate with how they did stuff. They knew how to do stuff, but they needed to advance. They wanted to use computers. They started to think about what we today call computer-aided design, right? Using the computer to actually make designs, to design them, to transform them, right? Think about taking this blueprint and converting it to a representation, something that the computer can store. If we're using pixel-based, of course it will work, but it will have all the problems that we told you about with pixels. So how do we make this work as shapes? Paul de Casteljou worked in Citroën in 59, and he came up with a method to actually encode these curves. He was working specifically on a new car model called the Citroën DS. DS is a pun because in French it means goddess. So this was a brand new car model, very pretty, lots of curves. How would he make it happen? He knew that he needed to take things forward. We actually saw one a few days ago, not far from here. It was the first time that I actually recognized the car model on the street. So new experiences, yay. He said Descartes' attempts to lay the foundations of analytical geometry ended in a flagrant failure. He raises the notion of algebraic degree to a level of dogma. This is not geometry. Casteljou wanted to make it practical. He knew what Descartes did, and he wanted to use it. He also used other ideas from back then. The spline is something that was used traditionally in a lot of engineering. For example, in shipbuilding, the spline is just a line that we use weights to make a curve with. So the weights are actually making up how the curve should look. And by coordinating the weights, we can reproduce the curve that we want. So he knew about this. He knew about Descartes' Cartesian progress, and he combined them to actually make the curves work. So as you can see here, the idea is quite the same. We have those weight points that we can use to make the lines work. The mathematics behind it is based on something that was done a couple dozen years before that by a Ukrainian mathematician called Bernstein. He developed the Bernstein polynomial. A polynomial is just a function that is made up of only simple parts, x power of 2, x power of 3, and so on. We like these functions because they're very easy to compute, right? Doing sinuses and other stuff is much more complicated. Mathematicians through the times before that were working very hard to make functions into polynomials. And actually the Bernstein polynomial was developed as a solution to take any function that is continuous and to represent it using a polynomial in as much accuracy as you can, of course, to infinity. That's what Casteljou was working on. So, how does it work? Let me give you a bit of intuition. We are taking the 4 points that we have, P0, 1, 2, and 3, and we are advancing to draw our curve. We're taking a ratio of each of the lines, right? So we have a ratio of, in this case, 0.14, between 0 and 1, between 1 and 2, between 2 and 3. We're cross-sectioning them using the ratio again, and we got the point. If we advance using this method, you get the actual curve drawn. So you can see it's not that complicated behind the scenes. And to actually compute it, we just use the polynomials because they're giving us the exact coordinates. This is just the intuition to make it work, and also the parameters that define the curve, because when we are defining this curve, we're telling it these are the 4 points, and we are getting it translated to a curve and vice versa, right? It's the exact same representation. Of course, we can advance it forward and use more control points to get more complicated curves, but we don't have to use that. We have other tricks like B-splines. You can look it up. Very interesting. A little bit about why it's called Bézier curve. Actually, while Casteljou was the first to actually develop this, he didn't get the credit because Citroën, the company that he worked for, didn't want it published. So Bézier, which worked for Renault, faced much similar problems. He came up with the same ideas, allegedly without knowing about them. And he got the credit, but we will still remember both of them, and great pride for France.
Yeah, both of them are French.
So, how does SVG work, we saw that, but how do we make it actually work for us, right? Because we don't want to write this code. What we focused about was how to render it, how we tell the browser, for example, how to create the construction. So you don't really need to do it by hand. Today you have lots of programs that you can use. Of course, you know some of them, Inkscape, Illustrator, Figma, but behind the scenes, they're all using the same method. You see here, the control points, they are the control points of the curve. And of course, computer-aided design is using much more complicated stuff, but behind the scenes, it's all very simple math. Of course, it's not that simple if you had to do it by hand, but it's actually very simple and intuitive. And it couldn't have worked if it wasn't so simple, because the computer wouldn't have been able to render it as you go, as you play with stuff. It has to be simple math in order for it to work. SVG has a lot more cooler stuff that we couldn't get into today. We'll have you the QR at the end. Just 2 more sentences.
Of course. So, what I try to convince you is that many stuff shaped the way we approach curves. The materialistic, you want to do it on a page, you want to do it on a computer. You remember Dürer, and we have our friends. The theory and curiosity of the Greeks and of Descartes, the society and economic stuff. We want graphics. Dürer wanted to sell books. I don't know, not really. And many, many, many other problems that we didn't get a chance to get into them. What I wanted you to understand is that you are all a part of a very, very long lineage of engineers that shaped the way we approach shapes. And be proud of your heritage, and don't let these academics think that they make the rules. Oh, let them, because then we can do cool stuff, and they don't.
I hope that now you also agree that the curve is your favorite line. You have no choice, because all lines are curves.
In a sense.
Thank you.
Okay.
So, thank you. We have 2 minutes for questions.
Yes, I've got a very simple and straightforward question. What is the name of the book of the Albrecht Dürer where you took all the snippets from?
It's we will get to it. We'll show it now.
Thank you.
I think it's easy to find, even if not to spell in the old German, but it's one of his most well-known. Can you?
And it's available online, so you can just read it, and you should. It's amazing.
If you had to pick a spline as your favorite, and it cannot be a B-spline or a Bézier spline, which one would it be?
Wow. Wow, I don't know. Ellipse? No, it's not a good... I don't know. Sorry.
Thank you.
Okay, thank you.
We're still here.
That was really great.